In this video, we are going to learn how to graph a quadratic function of the form f of x is equal to ax squared. We're going to first graph the parent quadratic function, f of x equals x squared. We're going to make a table and see what type of shape we get from plotting these points. So first I'm going to plug in -2 into the function. So -2 squared would give me 4. So I'll go to -2, 4. Then -1 squared, which is 1. So -1, 1. Then 0 squared, which is 0. So 0, 0. And then 1 squared, which is 1. So 1, 1. And 2 squared, which is 4. So 2, 4. And we draw a curved line through all the points, because the shape we're about to get is a shape known as a parabola. Now the trick to drawing a parabola is it's definitely curved, as this U shape, but you start to flatten out to like almost a horizontal line at this low point. You'll see here that these graphs are symmetric, so there is a vertical line straight down the middle of the shape that can cut in half and give you two mirror images. So every point on one side of this axis can be reflected to a point on the other side. Very important for graphing these functions. It makes it go by a lot faster. This is known as an axis of symmetry. And this very low point for a parabola is known as the vertex of the parabola. Now we're going to learn, we're going to get back to this in just a minute, but we're going to learn what happens when we apply a value in front of x squared. So if you remember our lessons on absolute value, these values should stretch or compress the function in some way, vertically. But let's start by plugging in some values. If I were to plug in 1, it would be 1/2 times 1 squared, leaving with a fraction. So instead I'm going to use 2, give me an easier point to plot down here. So we have 1/2 times 2 squared, so that's 1/2 of 4, which is 2. So we get the point 2, 2. And I'll skip another 2 to 4 and do 1/2 of 4 squared, which gives me 1/2 of 16, which is 8. So 4 eighths. So I'll plot all three of these points. So 0, 0, 2, 2, and then 4, 2, 4, 6, 8. So now I have these points, but that's only half the parabola, but we do know that these shapes are symmetric. So there is an axis of symmetry. It goes right through the vertex, and we'll split the shape in half, and I can reflect every one of these points. If this one's 2 off in that direction, I can go 2 off in the other direction and get another point. This one's 4 off to the right, so I can go 4 off to the left and get another point. And that can help me create my parabola. So I really only need points on one side of my parabola, and then I can reflect them all backwards to find all the points I would need. And I'm really just taking my time when I draw these parabolas. It's very easy to become lazy and just do straight lines between all the points, but that wouldn't necessarily look like a parabola. So I just take my time, make it as curvy as I can with a big U shape. Now let's look at -1/3 x squared. See what happens when I place a negative on this function. And here I'm going to use 3. So -1/3 times 3 squared. So -1/3 of 9 is -3. So I get 3, -3. And now I will also use 6. So -1/3 of 6 squared, so it's negative 1/3 of 36, which is negative 12, giving me 6, negative 12. And I'll be very careful when I graph these, because I'm going to count by threes here. So negative 3, negative 6, negative 9, negative 12. And I'll count by threes up here, so I can really find out where these points go. Negative 6. The first one I'll put at the origin. That's typically where a parabola will start. And we'll have 3, negative 3, so 3, negative 3. And then 6, negative 12. And again, these graphs are symmetric, so I have an axis of symmetry. It goes right through my vertex every time. And plotting points, I'll just count horizontally from the axis of symmetry. That's 3 points to the right, so I must go 3 points to the left as well, so that they are symmetric. And this one's 6 points to the right, so I'll go 6 points to the left. And now I'll have all my points to draw my parabola. This one's now opening downward rather than upward. So we've seen them open upwards. This one looks like it's opening downwards. So now let's talk about these stretches in compressions. Now I just talked about it opening upward or downward, and the way we tell is if that A value is greater than 0, meaning positive, the parabola will open upward, meaning there's no vertical reflection, and this vertex is a minimum value. So in the case with this problem, the minimum value would be y equals 0. And the other one, we have a negative A value, so A is less than 0. You're noticing here it opens downward, which means that we're going to have a maximum value, and there is a vertical reflection. So this vertex here, before 0 is a minimum, now y equals 0 is a maximum value. And just to show you where the stretch and compression comes from, when you take the absolute value of A, if it's greater than 1, this graph is vertically stretched. And if it's less than 1, it has vertically compressed. Now both of these, that value is less than 1 when you take the absolute value of it. So it has compressed. It has vertically compressed. And the way I can show this to you is if I were to lightly graph the original parent function, means 0, 0, negative 1, 1, and negative 2, 4, and then 1, 1, 2, 4. You'll see here, if I compare the two graphs, making this blue one this light, it looks like this red one's been more squished down. That's why it's so much wider than the other graph. So a wider arc means a vertical compression. Even over here, if I were to reflect these points, so negative 2, negative 4, negative 1, cause that vertical reflection so you can compare them. But still using the same magnitude, just making these all negative on the right. I'll see here, I can also tell this graph is vertically compressed in comparison. It's a lot wider of an arc. And that is how you graph a quadratic function of the form f of x is equal to ax squared.